Good afternoon, everybody. Thank you for choosing this talk to watch at this time. And yeah, I'm going to be talking about something that I have been uh, messing around for a couple of times now. And yeah, first of all, my name is Renan Araujo. I'm Brazilian. I live in Portugal. And I really like open source. So I'm an open source engineer at Very Good Ventures, a consultancy that exclusively works with Flutter. And I'm also open source maintainer at a collective that maintains some Flutter packages like the Flame engine and some others. And this collective is called Bluefire. I believe we got at least one of them here. See anyone else? I think that's just you, right? Yeah, thanks, Bluefire. But yeah, so that's it about me. That's enough about me. But yeah, so including this, the title of this talk, or whenever people talk about this feature, we describe it only as shaders. But that's not an accurate description because this is a very broad term, and there are lots of different types of shaders around. But the specific type that we're going to talk about today, and we mostly talk when it's involving Flutter, it's fragment shaders. But turns out that this is even not still a very specific description too, because fragment shaders are around Flutter since a long time ago, but now we can write our own fragment shaders. So in this talk, from now on, whenever I talk about shaders, I really mean custom fragment shaders. But it's a very big name to keep repeating, so yeah, let's go. So this talk is going to be divided in these parts. Each part we have some examples, except the last one, that's just a conclusion. And my intention here today is to show this feature from a perspective of a Flutter developer and what it can do for you. So whenever we start talking about fragment shaders and GLSL and stuff like that, we will see stuff on the internet, that's crazy stuff that people do, but they're not like that useful for people working with Flutter every day. So the idea here is to try to do some stuff that first is not possible to do without fragment shaders on Flutter, but also can enrich UI development. Okay, so first part, let's learn a little bit on what is a fragment shader in this context of Flutter. So the biggest, I think the only reason that a fragment shader exists is to answer a question. How will be the color of a pixel? Which pixel and what pixel, and where that pixel is, and what else can I use to define that color is in the second fact that a fragment shader works just like a function. So there's inputs, and the output is the color and the opacity of the pixel. The inputs are two types, the ones that we provide as values, and the ones that's provided by the framework. The one that's provided by the framework is only the coordinate of the pixel that the fragment shader will set the color. And the user-defined ones, they don't vary from coordinate to coordinate, so they're all the same for all the pixels in the screen. And yeah, they are just some two types on this case. So for user-provided input, that we call them uniforms just for the reason that it doesn't vary between coordinates to coordinate, is there's two real types of these things. Those are the numeric types, so they are based on floats or multiple floats. So from that, we have vectors and matrices, and lists of floats, vectors, and matrices. And there's also the texture inputs that we will talk about a little bit later in this talk. So the other reason, the other differential of fragment shaders is they run on the GPU. So the reason that the inputs from the user are not customizable from given the location of the pixel that's being calculated, it's because they run in parallel. So we cannot determine the results of one pixel and use that result for another pixel in the screen. It's always parallel, and the reason for that being parallel because it can leverage the GPU from that. So the GPU is a specific chip that exists to run things in parallel. They are really good at that. And well, that's what makes fragment shaders really fast. And another aspect that makes fragment shaders really fast on Flutter is because it's a way of bypassing lots of calculations that the engine has to do to define a color of a pixel. And then the engine can just rely on the codes that we write. And the code that we write is this. Okay. This is not Dart, people. Don't get scared, but yeah, it's pretty simple, actually. So this is a very simple, I think the most primitive fragment shader we can write on Flutter. So the first two parts, they are optional, but they're just the default values that Flutter uses, and I wanted to set there. So there are several versions of GLSL. Oh yeah, by the way, this language is GLSL, which is about, it stands for OpenGL Shading Language. And yeah, so that's the language. And the version that Flutter defaults is the latest one for 6.0, but we can define earlier ones. I really like to declare the version of GLSL. So in the future, when Flutter changes the default value, we'll know the targets in which the shader was dedicated to. And after that, we have the precision of the floats that we will use here, in either uniforms or internal calculations. And then we have the only import we can do. So there's nothing about creating a package and importing GLSL on a shader. The only one we can import so far is this one from Flutter that gives us the function that will give us the only inputs that we have that varies, which is the pixel coordinate. After that, we will have the uniforms. So here we have an example of two uniforms. One is a vector 2, so it's basically a vector of two floats, and then the texture with the symbol 2G. And after that, we have an out variable. So this will be the output of that shader. So whatever the value of that variable will have in the end of the execution of the shader will be the output of this file. Okay, so to add this on an actual Flutter application, there are 3 steps. First of all, you inform and you declare this file just like an asset on a pubspec, and then you load the shader, and then you apply the shader. And the way you apply the shader is in any canvas-like API that you can use on Flutter. And I can name, from my experience, that the main ones that we can use that is on Custom Painter, on the Flame engine, and also on custom render objects. So if you write your own render objects, we can use the shaders directly in the paints method. But yeah, auto-red render object is a complex subject. We have a talk only for that. We had a talk only for that. So this talk, I'm gonna focus mostly on Custom Painter and one use case that we used on the Flame engine. Okay, let's go. So there's also easier ways to load and to apply the shaders. So in this case, we have this package called Flutter Shaders that is, at least for me, it's fundamental. So if you're working with shaders on Flutter, install this. If you're gonna create your own shader, install this. It's gonna be really, really easy to simplify some stuff. For example, there's this way of passing the uniforms to the shader that you don't need to, let's go back a little bit. You don't need to control the index. So for example, here we're having shader set floats. We have to control the index of each float value. So if you're receiving a vector 2 on the other side, we have to pass in order each double value. And it's quite cumbersome if you have, for example, a list of matrices. So that would be like a lot of floats and a lot of indices to control. So you have this thing to, just set up our color. I really like the color one too that does some other operations. So, okay, I think that's it for talking. And now I'm gonna show an actual shader running. So I have this little application here to demonstrate. This is actual Flutter running on the right side, and on the left side, we have the code that's running. So the first shader is just this boring square, quite beautiful, but boring. So what's happening on the Flutter side of things, we just have a center, defining a custom painter with a definite size, and then we have a custom painter that we're just passing the size of the container to the shader. So if I go to first shader GLSL, we have the shader that's actually painting this thing. So we have the coordinate that comes from the Flutter helper that comes from the import here, and that will give us the position. And then we create this thing that's very important. So we are normalizing the coordinate. So it's always between 0 and 1. And the top left is 0, bottom right is 1, 1. So this allows us to have the same behavior on the shader, regardless of size and aspect ratio of the container. And then we calculate the 3 colors differently, the 3 channels of color, and then we return a vector 4. A vector 4 represents a color R, G, B, and alpha. So here is what we're doing. We can tweak around. So this is what we do, mostly with shaders all the time. It's just, I know, thanks for the try, Copilot. I don't want to do that. So for example, we just can change how the color is calculated just by switching some values and stuff. And by the way, as you've seen, we have hot reload on GLSL now, Flutter. It's quite interesting. And okay, so this is a very basic example. So just a bit of a summary. We learned what shaders are, essentially. We learned that it is fast because it runs where it should be run, on the GPU. So if you try to do that on the Dart side, it's going to be get really heavy pretty quickly. And it's numeric based. So inputs that are numeric based, we can do whatever, use all the techniques and concepts of math that we know to create visual effects. And one that I really like is interpolation. One of the techniques and math concepts that I really like to use all the time, not only shaders, is interpolation. So let's just give a little look, a very quick look on what exactly is interpolation. So the concept of interpolation is estimating a value that's in between 2 or more values, so it's a data set, given I forgot the name, interpolant. Yes, it's interpolant. It's very confusing. Interpolation, interpolant. So given an interpolant, we can know that I can estimate a value in between 1 or more, in this case just 2, and in between red and blue, we can estimate the color of the thing. So there are several examples of interpolation. So if you deal with widgets all the time and you want to animate something, probably one of the easiest things that we can use on Flutter to animate stuff is intrinsic animation. So basically, we have a widget around there, and we just switch a value, and the widget animates to the new value. For example, the animated container can animate lots of stuff. In this example, we're going to animate the size. So we have a width and a height that we set, and when sometime in the future do a set state, the container will animate its side. I know it's not a square. I couldn't animate to a square on Keynote, but anyhow, yeah. What happened here is that the framework interpolated the size of the container through time. So during that duration of 500 milliseconds, the framework on each frame interpolated between the old value and the new value. But interpolation doesn't need to happen only through time. Every gradient is interpolation of colors, but this interpolation happens through space. So in this case of the horizontal interpolation, we're interpolating between red and blue, given the horizontal axis of the container. And we can do that without shaders or anything. So interpolation on UI development is everywhere. Okay, so we learned that we can interpolate between this in time and and space, but there is a limitation. So whenever we are animating stuff, we can make the animation a little snappier or smoother. For that, we can control this with the curves. One type of curve that we really use all the time, at least I use all the time, is the easing functions that are based on the cubic Bezier estimation, I don't know, curve, right? It's a cubic Bezier curve that we can change how the pace of that interpolation happens. But yeah, so these are some examples that we have. We have the linear, that's the default. So how interpolation happens is on the top left, if you don't pass any curve. But if you can pass a curve, you can change the progress of the thing. But we can do that on gradients. There is no way to pass curves to gradients. So regardless of how many stops you have in your gradient, the interpolation is always linear. Don't confuse with linear gradient, that's the shape of the gradient. It's the interpolation of colors on Flutter is always linear, and it's boring. Oops. So here we have our second example, easing gradients. So yeah, we can interpolate all of those things. Let me show first the example. This is falling. I hate gravity. So example 2. Boom. So we have, I'm gonna go back to the example, and let's look into a little bit into the code. So we have here 2 boxes, all right? We have a normal. Is it great to see from people in the back? Is it visible? Oh, yeah, awesome. Yeah, that's true. There's a big thing there. Right, so we have 2 boxes, right? And we pass the same stops for both. But the normal gradient box is the normal way of doing a gradient, right? But there's a new one that I created here. It's the easing gradient box. So let's go to the normal one. It's just a container with a box decoration, borrowing from white to black, from top to bottom. And there's the easing gradient box. That's something different here. So we are loading a shader. It's called easing gradient. You just copy this to get easier. And we pass this to a custom painter, and we also pass an easing function. Okay, it's not a curve, it's a cubic. It's a subclass of curves, so we only support cubic Bezier curves for now. And then we pass this to the shader, and just look very quickly into the shader because shader codes can get unreadable really fast. So I don't want to scare y'all. And if you're going to explain everything here, you're going to take the whole afternoon. And we are still on the second example of 5. So yeah, this is the little shader code. And what we do here is we interpolate between 2 colors. So we calculate a new interpolant between estimation that we do via a cubic interpolation. So this is basically how an interpolation happens, and we go through estimation. So here we have 5 steps of estimation, and refine the result until we find the correct results of this. So this is the result. We have on the left side, we have a Flutter way of doing things. On the right side, we have the shader way of doing things. And this is happening because I'm passing a specific curve. Let me change here, example 2. So if we go back here, yes, we were passing ease, but we can change the curves to another cubic curve, and it will be all right. So gradients feels a little bit more natural when you use gradient things. So let me change to something that may make it a little bit harsher. So easing linear. It changes how the interpolation happens, and how this thing you have impact on the layout it depends on the context, for example. So we could try to replicate, in this case, change the stop on the Flutter way of doing things. But yeah, when we go a little bit harsher on the stops, it's visible when the gradient starts and finishes. So yeah, I would advise people to use easy ingredients, but we still don't have this as a package. I'm going to make everything open source in the end, so yeah, everybody can use. So yeah, we have our second example. We can use easy ingredients now on Flutter, and I don't know many platforms that support that. I think besides SwiftUI, I know that the web doesn't support easy ingredients. You can try to replicate that with multiple stops, but it's always be linear between stops. So yeah, it's quite interesting. Yeah, this is a simple example, right? We're just interpolating colors, it's changing how we do it, right? But on Flutter, we can see that if there is a framework that has lots of numbers that we can mess around, is Flutter. For example, we have scroll, factors, or we have, I don't know, gesture detection. But yeah, everything is based on numbers, and then we can interpolate those things all around. And with help of shaders, we can do this more richly. So yeah. So for the next example, I want to introduce that I really, really love gradients. It's one of those things that are weird someone to like, but I do like. I also like maps. So yeah. I really like gradients, and we have some nice gradients on Flutter. We have the useful linear, we have the beautiful radial, and we have the sweep gradient. That's nothing. And yeah, but what if we want some different type of gradient on Flutter? What if I want a gradient that progrades the color in a weird way, in a different way? So there are several ways. If you research on how many types of gradients we have tons of them. Some are simple, but why not we go for the most complex and the most expensive type of gradients out there? And this case is the mesh gradients, which will be our next example. But before that, a little bit of story. This company, this Spain company, little one called Stripe, they are really famous for their beautiful web designs on their websites. And some months ago, I guess, they added this thing to the homepage, and there's this little gradient thing, and that's animated. I really invite you to look into this website. It's pretty beautiful. And zoom out so you can see the whole thing. And yeah, we have an animated gradient shader. And they didn't have a name for that, so lots of people called Aurora gradients. Some other people called other stuff. But I guess now we settled on mesh gradients. And people got really obsessed with this thing, because if you Google mesh gradients, you will see tutorials like how to do the mesh gradients just like Stripe did. It's crazy that Stripe is also a reference on mesh gradients and payments. Doesn't make much sense, but yeah. But also, if you Google for tools that make mesh gradients, we have some, these tools that people do on their spare time. Weird people that do tools on spare time. And yeah, the thing is, the three most popular apparently tools, they're all different from each other, from the way you build the gradients, from the results. The results are totally different. You can look and you say, that's a mesh gradient. But what exactly is a mesh gradient? What's the math behind it? There's not much of a consensus there. Apparently there's a way of doing mesh gradients on Illustrator, but it's totally different from all of these tools. But one that really caught my attention was the Figma plugin. So the Figma plugin is just like that. You've seen happening there. So we have these little color pickers in the middle of the thing, and you can select colors for each individual of these pickers, and also for the start, you have colors for the corners, for the four corners. And then you can drag around these little color pickers, and you create this distortion. I really like that. But there's a problem with this. It is a Figma plugin. So it means the designer will enjoy this experience of creating a mesh gradient, and you click the button, and you have a JPEG. I want to animate the goddamn thing, and you have a JPEG? No, we are Flutter developers, we want to animate stuff, and we want to create beautiful stuff. So, yeah, we want to do this in Flutter. So the requirements here are we have the vertices, the little color pickers in the middle that we can move around. Moving around will create distortion of color, and we don't need to, but we can select individual colors for each of these color pixels. And also, this should be represented by a class that's totally numeric based, so we can easily create an interpolation between this. That's how we can animate stuff. And yeah, I think we got it, so this is how it's running. Let's go back. I think I'm gonna need the full screen here, so away you go, Android Studio. I want Android Studio to go, not you. Here we go, it's the example tree, so I have three little screens to show here. The first one is the editor, so we just start. Oh, it's really, I don't know if y'all can see, but I can't see anything from this direction. But let me make a little bit easier, so make I don't know, change the color of a corner. I think it's easier, right? Now, just see. So you have a little mix-up of colors in the four corners, but I can come here in the middle and select a color for one of these things, and then boom, boom, boom. I have a little button here to deform randomly the things, boom, boom, boom. We have had a little bug there. Nobody saw that, all right? Yeah, and then we can just write the thing and port this around. Notice that we have a little text here, but this is a representation of the entire mesh. And I actually prepared some here on Gist when I use the Seascape one. So lots of numbers, but if we pass here and set, we have a mesh. This is an actual mesh gradient that we select some colors, right? But, okay, I clicked too early. I shouldn't click on this. Yeah, there's a mesh behind. Yeah, so how this mesh works. So basically, I use another Flutter API. So this is the cool thing about shaders on Flutter. It's Flutter and shaders. It's Flutter awesome and shaders awesome. And yeah, on Flutter, we have lots of cool APIs, just like draw vertices. And we just combine with shaders to create this thing. So for example, here, we have a tessellation factor of 1. So basically, we have the quadrilaterals of the mesh. So each vertex of the mesh is like a 5x5 mesh, and the middle ones are the ones we can move around. So we have 4 squares and 4 squares, horizontally and vertically. And what we do with draw vertices, we generate triangles for each of these quadrilaterals. So for example, here I have in the bottom here, the bottom row, we have 4 squares and 4 pairs of triangles for each, 4 pairs of triangles. So a pair of triangle for each square. But we can do something that's called tessellation. So it's basically refining the mesh with more triangles. So we can do this and go crazy. The difference is on the result. So let me just hide the mesh and hide the color pickers to see how tessellation can make the gradient nah or or All right. So we have the thing, but it doesn't stop here because we can animate this. So the whole state of the mesh can be represented by this little string, and we can create linear interpolation between that. So for example, I wouldn't do this presentation without showing scroll. So we can create a mesh that grows while we scroll, or ungrow when we scroll back. Or are you prepared? I got this mesh that I just mesh gradient that I just showed you with the C stuff, and I created 3 meshes of that. The background one, it's actually the sky. It's the white part of the thing, the clear part of the skin, the thing. And then I created 2 meshes from the C side, in which the sky part has alpha 0. And then these 2 meshes, one has a wave in a form, and the other has a wave in a form, and I just animate back and forth. So we have a wave effect. And from that, I combined with a very nice and very advanced Flutter widget. It's called Stack. I just put one on top of the other and a text in the middle, and this is the result. We are animating like like an animation, and as we are dealing with the alpha channel too, you can kind of see the text, not in this horrible projector, but we kind of can see the text going down and disappearing as it enters the water. So it's basically two mesh gradients. And I can see that mesh gradients on Flutter has a lot of potential because of the things that we can play with Flutter, just switching around some uniforms, which are the inputs we send to the mesh gradients. And I guess that was our third example. Thanks. All right, summary time again. So we learned butter interpolations and how can we use them. We learned that a use case, in the case of easing gradients, that we can only do with custom fragment shaders so far, unless someone creates a pull request on Flutter and goes to the engine to change the built-in fragment shader. By the way, every gradient on Flutter is a fragment shader, but it's just a fragment shader we cannot write. And then we learned that we can also create something subtle and useful, like the easing gradient, that if some designers will see this thing, that's possible now with Flutter, some designers will really love it. We have a Figma plugin for easing gradients, but it's the same problem. It's a JPEG in the end. Yeah, we also learned that we can combine the power of shaders with other stuff, like draw vertices. And yeah, we can create amazing effects with that. Okay, so I only showed you that we can pass numbers so far to shaders, right? But I told you in the beginning that we can pass textures. And textures are literally bitmaps. We can pass bitmaps to the shader thing. So this is how it looks like. On the Flutter side of things, we will have an image, an instance of image. It's not the widget, it's the image from the Dart UI thing. And then we can pass through a different method on the shader. It's not a set float value, it's set an image sampler. And also, you have to control the index here, but it's a different index than the floats, so you can pass a bajillion of floats, and then we go to the image sampler. That has to be after the floats. You start from 0 again. But that's not a big problem, because you're probably not going to pass lots of textures through your shader, unless you are a crazy person. And then you receive on the GLSL side uniform, sampler TD, uniform texture. I mean, it's just a convention to start the names of uniforms with U. I like to start, I'm like a road person, I like to start the name of uniforms, their textures with a little t. So in this case, I use t texture. But that's just me, it's a me problem. Okay, so for the next example, it's a storytelling time. So I'm going to say something very complicated here. Some people will not agree with me, but the Earth is not flat. Nobody threw a shoe on me, so we are all smart people here. Awesome. Yeah, and because of that, that's a big problem. So that brings us a little bit of a struggle that we have since we started to make maps. I told you I love maps. I'm going to talk about maps now. So there's a really big problem of representing an actual sphere, or a surface of a sphere, or a geoid, in the case of Earth, on a plain paper. So there are several ways several models and different calculations that we try to find to represent that, but never with some kind of distortion. So this kind of distortions can bring some misconceptions. And there are really nice projections over there. Some of them are really familiar, like the Wagner 6. Some are very crazy, like this one. I don't know I don't know of anyone that uses this thing, but apparently it is a thing. And there are some lovely ones, and there's this one that I really like. It's called the equirectangular projection. And it's really great for shader people because the arithmetics of it, it's pretty simple. The meridians, the coordinate system that humanity uses, it stays unchanged if you compare, if the x and y axis, x and y coordinates of this image. But there is a problem with that. I told you there's distortions, so there's a little bit of a misconception. So, oh yeah, third thing I like, planes. I really like airplanes. And I was looking, I downloaded this app that we can track planes flying, like live. It's pretty cool. Not a terrorist, but it's pretty cool. And basically, I saw some planes doing some weird trajectories. So, for example, I saw this plane that went from New York to London, and yeah. So planes, they supposed to go on the shortest route, right? Like this, straight away. So I thought they would fly like this, right? Yeah, but there's a problem. The Earth's not flat. So the actual trajectory of the thing is kind of like this. This little curve. And that's kind of weird. It's kind of, disconcerting that thinking that this thing I've seen and looking into it as a picture of the world for my whole life doesn't quite represent the things as the way I thought. So, yeah, there is one thing interesting about this projection is that from the very center, all straight lines are actual straight lines above a sphere, like real-life straight lines, but just the ones from the very center. And unfortunately, we chose the very center of our maps to be in the middle of the ocean, which is quite weird. So I made a shader to change that. So basically, from this one, this example there, it's not flat, we start with the literal image that I show on the slide is I'm using as a texture here. It's something that I got from NASA. And yeah, it's pretty common, right? It's the same map. But what I'm doing here is I have one state that is a vector 2, and that is the actual coordinates of the center of this image. So right now, if you look into here, it's very small here, but trust me, when I have my cursor, it's 0, 0. So we are in the center of the Earth. But we can drag around. And things can go crazy if you drag around, not horizontally, but vertically. So we can change the way that we center, and it's the same projection, but we're just changing the center of the map to something else. So basically, there are several ways we can look into Earth right now. For example, this is the world according to some American movies. And this is the world, a world map that will never forget New Zealand again. All right. And yeah, it's pretty cool. So what's happening here? I don't know if I show code. Do we have time? I don't know. I'm not measuring. We have time? Don't know. So let's go. Let's go see the code. Whatever. Hello, Android Studio. And never talked bad about you. So we have an equirectangular projection. GeoSL. This is the one I want. So what's happening here? It's kind of cheating. So we have some nice functions. By the way, these functions, I wouldn't be able to write those things without the work of open source people. So I always research on Google or ShaderToy to see how people are doing some stuff. So for example, some of these functions here are not of my authorship. It's from open source people. But here we go. We have this. This is the way I like to call the shader. So basically create a fragment function that I can do pre-processing and a post-processing afterwards. But I'm not doing that now, but that's my boilerplate. And what we do here is we have basically a sphere with the size of the UV thing. And what we do in the end is first we scale, because in this shader example, we can zoom out and zoom in. So this is the logic for scaling the sphere. But also there's the equirectangular remap. So what we do is, okay, we pass, we convert the vector 2 that we passed through a uniform into an actual position in a sphere. So we basically transform the texture in a sphere. Then we rotate the sphere on the z-axis, on the x-axis, and the y-axis. So the y and x come from, the x and y that are inverted here come from the coordinate that I showed. So if you're going for the coordinate 45, 45, we are rotating the sphere on that. And then we go and transform the sphere back again to a plane with inverse equirectangular projection, x, y, z. Why are you looking at me like that? And yes, we kind of have it. Right, so this was the example. So let's go for the final technique of this afternoon. So basically, I showed you all that we can pass an image. In this case, it was a JPEG that I got from NASA, and pass to the shader, all right? But we don't need to get an image that's saved as a file. We can actually use the user interface of a Flutter application as input for a shader. And for that, we use, again, the Flutter shader packages that has this amazing widget that does this. Let me explain. We have some widget as a child, literally some widget, and we will render this thing. So this is what animated sampler do. It will render this, but will not put the resulting picture in the screen. So before that, it will run this function over here that receives the resulting image as an actual image instance, and you can pass that as an image sampler to the shader, and then also receives a canvas that will actually paint the thing that will go to the screen. So you receive an image, we can manipulate that with shader, and then paint something else, the results of the shader, in the screen. That's pretty straightforward. So this brings us to the next example. So next example, story time again. So if you drive and you associate this with car, you'll probably hear the sound when you do the turning lights, right? BMW people will not know what I'm talking about, but yeah, when you turn on the turning light, it's a right? But yeah, that sound today is totally made up. The lights doesn't, the little bulb that turns on and off this thing is totally silent. But this sound has origins back then when they actually use it in incandescent lights that turn on and off when you're trying to turn and trying to sign to the BMW guy that you should turn, I don't know. And yeah, they kept the sound. So this modern technology resembling some kind of, it was a bug, I don't know, a bug that became a feature of old technology. This, there are lots of names out there. The one I really loved is nostalgia engineering. And nostalgia engineering can come from utility, which is the case of the blinking lights, or from aesthetics. So this day and age, people buy films and buy film cameras to take pictures with films because it's different, it looks different, has its aesthetics. In the case of the film industry, they still use that because of the dynamic range. It's still way better than digital sensors. Also, there's still people that uses vinyl, big vinyl discs to listen to music. So there are several examples of nostalgia engineering happening there. And we're gonna have one more here today. So when we go and look on pixel art, we look at pixel art today on LCD monitors, and they don't look how they're supposed to look. If you play Mario on the best TV, it will not look the way it was supposed to look when it was released back then. Because CRT displays, they render images in a different way. So the way the pixels are painted on the screens are different. They smooth it out some stuff. This kind of smooth it out cannot reproduce sharpness the way that modern displays can produce. So basically, they use this kind of non-sharpness of things as kind of a feature. And yeah, so the problem is, the bottom line is that Modern displays are too good for us to enjoy pixel art the way it was supposed to. Not even only pixel art, but some low sharpness images like this one. So this is an actual photograph of a CRT display showing this image, and you can see the zoom here, that each pixel is totally different. And it's crazy that, and you look just to a subsection of this image, and you cannot imagine that the resulting image will look like the thing in the left. But yeah, so the idea was here on trying to create something like a CRT display on a LCD display. And yeah, we go for the example 5. Let's go back here. So this will be our last example of today. It's called Nostalgia Engineering. And this is well kind of the result, you know. I don't know if you all can see it, but we have a different disposition. Let me try to change this. Let me make the pixels as big as they can be. So this is kind of a zoom in on the thing. We are calculating the resulting color of each pixel as a sum up of all the pixels that we have in the original image, and grouping up in this little kind of egg-shaped thing. So I was first going to use an oval, like ellipses, for each pixel, but these things are actually textures that I manipulated myself on a vector editing program, and use it also as a texture. So we're having a bitmap texture that comes from Flutter assets, but also the UI. This is an actual UI, so we have a scroll view back here that we're just scrolling here now, and we're applying the shader. And yeah, this is my little CRT shader, and we can sacrifice a little bit of sharpness for the sake of a retro look. By the way, this is the only shader that I showed today that's in production. So if you go for the Flame Light Runners game that's on the Invertace booth, I think I have a slide for that. Yeah, if you go for the Light Runners game that's on the Invertace booth, right now it's running this shader. The pixels are very small, but you can see that has its own kind of CRT-ish look. I'm also going to let this laptop on the VGV booth, so you can see these examples live. So yeah, tag along on the VGV booth, and we will see. Okay, so final summary. We learned that we also can pass images. We learned that we can use the graphical results of an entire Flutter UI as a uniform, as an input to the shader. And we can also bring retro aesthetics to apps, and in this case of Light Runners, games too. I didn't even go deep on game development, because I guess that's something else. If we can do a lot on applications, on games, it's just the sky is really the limit. And yeah, so last part is go seek help. So this, if you're looking to shaders and don't know nothing about shaders now, the 3 main things that I recommend is first, the Craig video about custom shaders. So he goes a little bit deeper on the association of Flutter and fragment shaders. There's also the book of shaders. That was a recommendation by this guy for me. This is the thing that I use to learn shaders. And it's really, really cool. I think this is one of the best programming books ever, in my opinion. And it's totally online. I don't need to buy anything. It's totally free. And there is playgrounds that you can play around without having to create an entire Flutter application just to play around with shaders. And obviously, the Flutter Shaders package, that's fundamental in this day and age. And yeah, every example that I showed here, and a lot more that I couldn't have time for today, will be open sourced, and I will create either Twitter threads, if Twitter doesn't die by then, or anything, blog posts, anything, as a guide on how to implement them and use them. Some of them, like the mesh gradient, will be something more than an example. I'm actually shipping that as a Figma plugin, and ways of people creating and sharing and reusing mesh gradients. And I guess that's it. Thank you.